we should get started. Okay. So we have the same schedule as yesterday. My name is Xinfang. I'm chair this morning. The first talk is Professor John Doyle about the particle physics of molecules. So
you want to quickly announce the change in the schedule?
I'll change it. Yes. So the second speaker, Dave DeMille, he can't make it. So I think Amar and Zach will give the talk. So there will be actually 3 talks this morning. But yeah, again, Professor Doyle, please.
Professor Doyle. All right. That's what I'm talking about. All right. Is that too loud? You're good? Okay, great. Good morning. Thanks all for coming. All right, where am I going to start? I'm going to start with this. So I'm going to skip over a bunch of things. There was a number of talks yesterday. There'll actually be a couple of talks after me. Like for example, Eric's talk really put EDMs in great context. So I'm going to kind of blow through very quickly. Although through the demands of the chair, I will show how the ACME experiment actually works. So I added that back in at the last minute. So just talk about what we do in my group. Essentially what we do is we think that we can somehow use molecular complexity to make an impact on the 3 areas of science: precision measurement, looking for physics beyond the standard model, understanding cold, ultra-cold, and quantum controlled collisions in chemistry, and quantum simulation and quantum computation. And one of the big questions here is, can we actually control these molecules? Do we have single state control? And then a broader question is actually, can you use the complexity of the molecule to your advantage? Actually, even though they're harder to work with, they may, in some cases, be better than atoms. So I'll be talking today almost entirely about this. It's precision measurement. And just to remind you very quickly, there's 2 big mysteries. What is the dark matter? We know it exists through gravitational observation or observation of the cosmos. And why is there matter-antimatter asymmetry? And if you want to take a step back, it's really this paper from 1967 by Sakharov that laid out a formula which apparently people still think is correct, that you need a certain amount of CP violation or time reversal violation at a microscopic level to describe the matter-antimatter asymmetry. And the standard model does not have that level of CP violation. So one of the ways that you can explain those 2 things is you take the standard model particles, here these boring ones in solid colors, you add these exciting new varied particles that generically have CP violation associated with it. I gave that colloquium at MIT yesterday, so it kind of prepped me a little bit, made me think about some of the things that we assume. But I would say the following, when we look at for EDMs, we're looking for particles that have CP violation associated with it. And you think that might be special. It's quite the opposite. In all of these beyond the standard model theories, that kind of CP violation just naturally occurs. So if CP violation is somehow suppressed in these beyond the standard model theories, there better be a really good reason. And maybe there is, but there better be a really good reason. All that being said, we don't know what's going on in particle physics right now. It could be literally a vast wasteland of nothing between here and the Planck scale. We hope that's not true, but that's possible. Okay, so to remind you, we are looking for the electric dipole moment in this experiment of the electron. Here's a simple single loop Feynman diagram. This is the back of the envelope formula for the mass of this particle. And here's the CP violating phase for this particle, and the mass squared is proportional to this sine of this angle. If you just look in your head, if you look at this and then move the constants around, there is a mu b in there, the magnetic moment of the electron, and that's another way of expressing it. So the ACME experiment, this is an update. This is an update on the ACME experiment. This experiment is now in its 3rd generation. And I'd love to tell you about it. So we're looking for these things by looking for the electric dipole moment of the electron using dehydrated molecules. So one of the things I want to get out front, it's very important getting the experiments actually done. there's details that matter. And one of the details that matters are these things. So in molecules, you can have orbital angular momentum along the internuclear axis. And certainly when even as graduate students, you're not taught about the molecular frame, but there is a molecular frame quantum number, which is the projection along the internuclear axis. So if I sit in the molecular frame and I do a parity transformation in the lab frame, the direction of that angular momentum switches. And what that means is that if you ignore perturbations, there's two degenerate opposite parity states when you have orbital angular momentum along the internuclear axis. One way of getting that is that there's actual electrons going around a diatomic molecule that give you orbital angular momentum. It's like you learned about in the first semester of quantum. These states turn out to be special. In fact, in the ACME experiment, the state that we use is the metastable state in order to get this projection. These orbital angular momentum projections are generic, however, in polyatomic molecules, either the projection of angular momentum due to a bending mode in the molecule, that's the middle diagram, or the projection due to a spinning, say, methyl group, which is here. And depending on, they just labeled it with different quantum numbers. Okay, love you, that's it. The bending mode, hope everybody sees that. You have a molecule bending like this, or it can bend like that. I add those two, and that means I can do this. And so there's actually 4 quantum numbers that describe vibrations for a triatomic molecule. 2 stretch, 1 bend, and then 1 projection of the bend along the internuclear axis. This gives us beautiful alignment of the molecule versus a applied lab field. And these are very, very low fields, very, very comfortable to work with. And you get this kind of near ideal structure, the molecules pointed this way for this state, this way for this state. And this is kind of like a zero dipole. So if you're thinking about qubits, this screams out to you as being like fantastic. So EDM experiments, the Doyle experiment, our experiment rely on this switch. I want to say rely on, it's wonderful that we have this switch, I guess is the one way of saying it. If we didn't have this switch, could we do EDM experiments? Yes, we could. But this is great for rejecting systematic errors. And it's very hard to talk about systematic errors in a talk like this because I could talk about systematic errors for an hour. So we spend most of our time thinking and dealing with systematic errors when we're actually doing these experiments. And so that's why this is important. Very quickly, here's our molecule, thorium oxide. Thorium is radioactive, but not very radioactive. Just don't breathe in the dust, you'll be okay. It has an effective electric field because it's heavy. It has an effective the electron sees an effective electric field with essentially an atomic unit, 10 to the 10 volts per centimeter. And so how do we do the experiment? We just switch the molecule direction back and forth. We leave the electron direction the same, and then we look at the precession of the electron in the lab frame with an applied electric and magnetic field. So I put on a magnetic field, the spin's precessing around. I put on an electric field, I polarize the molecule. Now the effective electric field can be pointed this way, one orientation of the molecule, or this way. And if there's an electric dipole moment, the interaction between the electric dipole moment of the electron with the applied field will be different, it will be opposite sign depending on whether the molecule is pointed this way or this way. And to the magic of lasers, we can interrogate this state and then just tune our laser to interrogate that state. So it's wonderful. All right. I'm glad somebody got that joke, laser joke. It's from a movie. No, not it's early. Okay. So yeah, it's a metastable state. It's got a 5 millisecond lifetime. So this, of course, limits our coherence time for this spin precession. That's okay. And as I was fond of saying, an EDM experiment is a clock with a switch. We're just, measuring that space between 2 quantum levels. And we just really try to do it really, really, really well. And then we switch the molecule around and we do the same thing. And so, as I'm also fond of saying, if you look at clock, progress in clocks, all the progress in clocks will eventually end up showing up in experiments like this. So here's a layout of the experiment, ACME 2. Here's the cryogenic buffer gas beam that produces our molecules. interaction region, you can see is about that long. We prepare the molecules here, leave them out here. There's some lasers here, and this is is my lab. Sorry, is my lab. This is still my lab in Lisa building, but now that this has all been moved out, I'll talk more about that. But while I was running, the lasers were actually in Jerry's lab and was connected by a huge bundle of fibers, and that worked really well. So don't be scared of connecting two labs together with fibers. So here's the movie, popular demand. So here's our cryogenic buffer gas beam source. We want to keep the magnetic fields from varying too much, because if we apply a magnetic field to get the spin processing, if we have variations of the magnetic field due to the environment, that will kind of mess up our experiment. So we have these multi-layer shields. We get down to, well, we hope to get down in that experiment to less than 10 microgas, but we ended up being around 100 microgas. Wasn't so great in the end, but it worked. And so we have these targets. These are ceramic targets of THO2. This is this quote unquote stable form of thorium oxide. You have this very violent event through the application of a 4 nanosecond, 50 millijoule pulse. It vaporizes the THO2, creates THO. It thermalizes with cold neon gas, goes through a hole, and then we form a beam here. So we're really, now just pure molecular beam experiment. And in this region, what we're doing is we're applying some optical pumping and some microwave simply to increase the number of molecules in the state that we're interested in the EDM sensitive state with the particular rotation. So here we use optical pumping and styrap to orient the electron spin. And you can see we have an applied magnetic and electric field. And then the molecules go from here to here. You can see this spin process, and it's processing because it's in a magnetic field and because there's an EDM. That will be the other thing that makes it process. And then we read it out by simply projecting the spin along the X and Y axis in the lab frame. And that's how we can figure out how much it processed. Pretty straightforward. The transit time in ACME2 was about 1 millisekond. So here's this is from SNOMAS, the electric dipole moments. This is like the best ones. I'll show you the ones with the Doyle in just a second. This is trying to convince science physicists to support us. It's been working so well. And so we improved over the previous result by an order of magnitude in ACME1 and order of magnitude in ACME2. And you can see this according to this report, which is written by many, many wise people. This is going to be what's going to happen. You'll notice there's these little bars along here that have TeV on it, and I'll describe that. As you heard yesterday, the current best limit is set by the hafnium fluoride Gila experiment. That's here. And again, you see these bars, these TeV bars over here, and Eric explained that. But this is pretty nice progress. Steady, we'll call it steady progress. But there is something that happened. I didn't put the plots for the accelerators. They kind of the accelerators are kind of doing better than us in this, in probing for new particles. And then something happened. The accelerators went here, flattened out versus time, and we kept on going. So right now, at least for reasonable CP violating theories, we're doing significantly better than what the accelerators are doing. Here is now in theory space. Here was ACME2 here, and here's the Gila result. And these are a number of theories, not the only ones, but they're the ones that are most favored or have some kind of, I don't know. At this point, they feel good to some large group of people. Susie really was extremely well motivated. And the idea of seeing something around the TeV level really makes sense because of the Higgs math. And of course, the high energy people think, well, they ruled it out with the accelerators. Well, in fact, we did a pretty good job of ruling it out with the EDMs. And so the combination of those two things, it looks like naive Susie is in dust, and then you have to kind of come up with variation. This actually is quite popular around Harvard, this minimally split Susie. So that was ACME2, and then there was the ACME faculty shuffle. And so Jerry Gabrielis went to Northwestern. Jerry Gabrielis was here. He went to Northwestern. He was at Yale. He went to University of Chicago. And this worked really well. They would come up every couple of weeks by train. But we decided when this happened that we would have Acme 3 at Northwestern for many good reasons. And now I go there approximately once a month physically, and then of course we meet by Zoom. And so now the band is really going to break up the now a professor at Hopkins. So this was Acme 1 and Acme 2, and I don't know whether I say it here or I say it the next. Oh yeah, I didn't go nowhere. Boring. That turned out to be, I just use the word brilliant to do this. It turned out to be brilliant. And of course, we knew that. No, it was brilliant partly because of the pandemic, but what we ended up doing was really leveraging exactly what we needed at exactly the right time. The Acme 3 apparatus is entirely new apparatus. So what we were able to do here is keep the Acme 2 beamline running. We were able to use Acme 2 beamline to test out the molecular lens that I'll talk about, the Q state magnetometry that we talked about, measurement of the thorium oxide lifetime. It turned out to be longer, and allowed us to make a longer apparatus, longer coherence time, and build the lens and the new beam source here while the main interaction region and the magnetic shields were being built at Northwestern. And there was not space to do all that at Northwestern. So it was just like this kind of adiabatic, movement there, and it really worked incredibly well. I was just really thrilled with it in the end. Here's a picture. Also, we had, as I'll note at the end, we also had extremely good people working on it. So here's the interaction region. You can see it's bigger. If you notice the size of the last one, it's bigger. It's kind of this square kind of approach. There's a lot of work that went into this. I'm afraid of giving credit to people who did each one of these things because I'll forget somebody who did something. But there's many people in this room who deserve the credit for improvements in this. So here's the interaction region. Here's the molecular lens, and here's the CBG to the new CBG. The upgrades: new beam box, new molecular lens to focus molecules into the interaction region, basically capture more of the molecules that come out of the source. We have longer precession region, instead of being around 1 millisecond, precession time is around 5 milliseconds, and we have better photon detectors. So the photon detectors were developed at Okayama University, the new collaborators going from Acme 2 to Acme 3. And that plus improving the collection optics really improved our signal significantly. These silicon photomultiplier units are custom units built at Okayama. They are absolutely fantastic. So you go ahead and look them up. Has higher quantum efficiency, and we truly love them. They were engineered very, very well. Then we have this electrostatic lens that focuses the molecules again from the source into the interaction region. You can see we get an increase by turning the lens on of about a factor of 10. And that results in this kind of data. Here's the Acme 1. So we have this pulse of molecules come through. As you saw, we do the measurement. So this pulse is some number of milliseconds wide. And here's the Acme 1, here's Acme 2, and now that's Acme 3. So we've greatly increased. And this slide, you can see there's a person in there. See that part of the person? And they're looking at one of the light guides. We have light guides, we have 8 light guides coming out of the detection region into silicon photomultipliers, and you can see this by eye. So it's a bright signal, and it doesn't hurt that it's green. And for those experts out there wondering, where is it, looking at Acme data, there it is. We're taking Acme data as this top-notch data. Of course, we didn't forget about systematics. Never forget about systematics. A lot of work went in to the field plates. We need longer field plates. We need to make sure that those field plates have low non-reversing E field, low patch effects. They have to be flat. We have to worry about polarization gradients. So we have to worry about birefringence in our beam. That was one component that led to one of our biggest systematics in Acme 2. And the magnetic shields, as you increase the volume of what you're trying to control, it gets harder. And so these shields were put together using the best approach that we could. They're very complicated. This does not give justice to what's going on. There's a bunch of coils in there for trimming, for applying the magnetic field, for keeping the gradients low. It's very complex, and this all works, as you'll see, and we have really very good suppression of the magnetic field. So that all worked great. Then we have this Q state magnetometry. You know, the H state is great. It's got cancellation of the spin and orbital angular momentum, so it's got a very small G factor, which means that the molecule is insensitive to magnetic fields. But if you put it in the Q state, you put it in the most magnetic state. I'm not sure if that's true, but a very magnetic state, and that's actually a very magnetic state of the molecule. And now you can use that molecule in situ for doing magnetometry, which we like. You put all that together. Here's the EDM sensitivity for each one of these improvements that occurred. The proposed sensitivity was that, and we've got it. So we have the statistical sensitivity we were aiming for, and maybe even a little bit more. You can see this. Average over 1 second. It's bright. We set the blind a month ago. Push the button. To be honest, I think that I set the blind, but I'm not sure. They have, you know, they wheel in the PIs, right? And everybody's kind of, yeah, they're taking pictures of it. You push that button. Okay, now the blind set. It's like, yeah, okay. Maybe I set, or maybe we set. Sorry, yeah, I set the blind. Maybe we didn't. Okay, but we're taking EDM data, and the first systematic checks are actually underway. So that's the update. Where will that sit on this plot? We're really starting to intersect with some new theories, just minimally just look at SUZ, for example. About an order, we hope for about an order of magnitude improvement over the current best, which is the Doyle result. So just put a point there, so there. That's what we think, projected. These are all the people that have contributed. Jing Wu is here. Who else is here? Hugh Bond is here. Zach is here. And I'm here. Okay. Nick, yeah, there. I was getting the last Nick's here. Great, thank you. And this is the current on the ground team. So this is like the people actually making the experiment work like right now. Great team, incredible team actually, incredible team. So what's the future of CP evaluating searches? Where are we? Okay, great. Well, how do you improve? You improve by either, making, in this case with electron EDM, you make a higher effective electric field. We can't do that. We're really kind of an atomic unit for a molecule. But you can also, in your mind, replace this E effective by improving the intrinsic sensitivity to CP evaluation. You can increase the coherence time. This is Eric's favorite thing to do, and I believe him. I agree with what Eric. I would love to have longer coherence time for all the reasons Eric pointed out. Or just increase the number of molecules. That is always fun. If you want to increase the number of molecules, you tell that to an experimentalist. It's like telling a stockbroker, how do you make money? You just buy low and sell high. You just work at it, right? You do the best you can. So not much to say there. But increased coherence time, we want to kind of go from the millisecond regime to this 10-second regime, which is achieved in ion traps or optical lattice clocks. So that would be ideal. And this there's a paper, Nick and Yvonne wrote a paper, basically kind of laying out a program for doing this. You take, say, a polyatomic molecule. Here we have this polyatomic molecule, simple one, triatomic with the bending mode, using this orbital angular momentum to get the structure, which was so useful in ATME and so useful in JILA, the JILA work. And then put it into an optical lattice. You need to get these polyatomic molecules ultra cold in order to put them into an optical lattice, or I just say optical dipole trap. Figure out which might be better, or tweezer array maybe even. But you need ultra cold polyatomic molecules. How are we going to get there? Or what else have we been doing in our lab for the past 10 years? And that is, we've been working on these things, of course, as I mentioned. And we have been using laser cooling. So we have the CBGB, which you're already familiar with. So if we run this with helium at very low temperatures in order to make the molecules slow enough, we can do laser slowing, put them in a mod, do subdoppler cooling, put them in an optical dipole trap, and then put them in a tweezer array. We're doing quantum information. Using calcium fluoride as the first molecule we laser cooled for pedagogical reasons. So here's the ground electronic state. Here's the excited electronic state. There's an ionic bond, so the leftover electron is pushed away from this fluorine over here. And that's the ground electronic state, inside electronic state, that's like an S state, that's like a P state. And so when you excite it, it really doesn't change the bond length very much, which means most of the time, if you excite it to this excited electronic state, it will just go back down to this original vibrational state. But once in a while, every 50 photons, it will come down here, so you need to add another laser. And then if you add enough lasers, you can scatter out, say, 100,000 photons. And to put things in perspective, you need about 10,000 photons, 20,000 photon scatters to do all of that physics I'm telling you about. Slowing, Mott, subdoppler, all of that stuff in detection. It is an extremely pretty experiment. All those colors. Wonderful. So here is kind of a summary of what we did with calcium fluoride, made an optical tweezer array. We studied collisions and actually were able to control these collisions with microwave shielding. And this particular work then led to other groups doing this and actually having great success in making quantum degenerate gases using this microwave shielding approach. We in fact showed qubit entanglement, fidelity above 0.5, and we have recently done Raman sideband cooling to emotional ground state. There's lots of reasons for using molecules that some of you know. But I would point out this is kind of very interesting, this error correction protocol using molecules, including polyatomic. I had to put this slide up because it's so cool. So here is, using quantum information talks, new qubit platform molecules. Here's the time between first single particle control to when the 2 qubit gate was made, and then here's the fidelity as a function of time. The time between that for molecules first control to a gate was very short, and then you have this rapid drop. And there's theory papers which argue that molecules will have extremely high fidelity, including by Confine Me here at Harvard. And we expect those papers say that we should be able to get down here. So that's exciting. But for full disclosure, the coupling between molecules is fairly weak. It's on the kilohertz level. It's not gigahertz, but it's certainly an interesting thing. It's an interesting development. And one can think about using these polyatomic molecules in exactly the structure I talked about for qubits also. And they may have some advantages, but it doesn't matter. To be honest, I don't care whether they have advantages. It's just cool. It's interesting to think about how we can actually use these molecules to do quantum information. Maybe it will be an advantage, maybe it won't, but it's science, it's basic science. There's other reasons for, of course, studying polyatomic molecules. So how do you do it? Basically, you just replace that fluorine with a pseudofluoride, you have the same bonding structure. At least this was the kind of the idea that we put forward. You could just change out this OR, this oxygen radical group, and this electron would be unaffected, so you should be able to laser cool it. Now we're going to take 6 years of work and compress it into one slide. Here's CaOH. Here's the level structure. Turns out we need a bunch more lasers, so we have about 12 lasers right now, something like that. Any CaOH people here? Yes, I get it. Thumbs up. 12 lasers. You think, oh, 12 lasers, oh, that's a nightmare. It's not really a nightmare. And one of the reasons is these fiber lasers with the SFG, they're super reliable. And many of these lasers are actually low power too, so higher refund. Made a magneto-optical trap. We did subdoppler cooling. We put them in an optical dipole trap, and you're actually seeing a tweezer array of single CaOH molecules. So that's where we are with polyatomic molecules as of this year. So we can use polyatomics for dark matter and EDM searches. Yesterday's talk was by Nick. Next talk by Zach, and I hope I didn't forget. Maybe there's some other talks. I don't think so. As you heard, what's the next 20 years of improvements? We really have this new op-amp. I feel like Hans Dano. I'm going to put everything in terms of an LRC circuit. So we have an op-amp, a multiplier. Remember, I said that you can think of, you can put in the intrinsic sensitivity of CP vibration, and these optical deformed nuclei have this higher intrinsic sensitivity to CP violating physics. That's the idea. There's a number of collaborations which have been formed over the past few years for very, very good reasons. This is incredibly interesting stuff. It was basically if you want to think about discovering particle physics, you should think about doing an experiment like this. So, and like I mentioned, there'll be a workshop tomorrow. You're welcome to come. If you haven't already signed up, just show up on this. It's a kind of technically oriented, really trying to get time for people to talk about the nitty-gritty of these experiments. So where do we put, where does that put us? With SROH and YBOH, poly-EVM, which I haven't talked very much about, but you'll hear more. Or you've heard some, and maybe you'll hear more. But here is where we are with, oops, I wanted to change this. Not RX, but just any of these experiments that I showed before. You're up here, there's a gap. You're basically traversing particle mass going up to extremely high values on the order of PeV. That's what ultimately these experiments, whether it's RAX experiment with radium or another experiment, will end up. And really, this is the future accelerator plan for 2055. So this is an amazing amount of discovery potential by using this kind of work. And you think, well, okay, but what is, are there theories? There's some actually pretty well-founded theories by just looking at the Higgs mass and making some basic assumptions. I point you to this paper, not that paper, this paper. You're basically saying, yeah, you kind of expect the new particle to be at very high masses, above 10 TeV, up to 1,000 TeV. And this is where, and this is the only game in town for getting to that mass range. So I want to talk about an important technical goal. I think I'm out of, no, okay, so it's 40, yes, so I got 5 minutes. Okay. An important technical goal. This is very technical, but I love it. Important technical goal. So all these experiments, if you're doing ultra-cold molecules for EDM, you want to get as many molecules as you can, right? That's the N, 1 over square root of N, at least without entanglement. And these molecules are precious. So the question is, and we want to do these experiments in an ODT. So we want to get all of the molecules that we have in our MOT, and of course, we're always working to improve our sources to get as many molecules in the MOT as possible. We want to have the efficiency going from here to here. We want it to be 1. We want it to be unity. That's what would be ideal. And so I want to tell you about the conveyor MOT. This was discovered through simulation, and then in my group, and then we did the experiment. Let me say quickly about type 1 versus type 2 transitions. Type 2 transitions are what we use for molecules. We have to do that because we have to get rotational closure. And in the typical type 1 transition, which is where the here, actually I should go forward. Let me show you the diagram. Right, so here's a type 2 transition. Type 2 transition is fewer angular momentum states in the excited state than the ground state. That leads to dark states, but this is what it allows us to give a rotational closure, and this was first pointed out by Doyle and collaborators some time ago and led to really one of the things that sparked starting laser cooling. So in a typical type 1 transition, on the other hand, you have, here's a function of velocity, and this is for a MOT and force, you have this kind of structure, so you have this well-known subdoppler cooling, which happens at low velocities, and you have Doppler cooling, which happens at high velocities, and this is all just wonderful for a MOT. For the type 2 transitions, what we have is Doppler cooling, but the structure is such that you end up with subdoppler heating if you're red detuned. So here you're red detuned, here you're red detuned. And so what Mike Tarbutt and his collaborator pointed out is that if you flip to the blue detuning, that you actually get subdoppler cooling at low velocities. And so the idea, this is called the blue MOT, is that you capture the molecules first in a red MOT, you bring them to low velocities, and you turn it into a blue MOT, and then you're able to compress and cool further. And this was really a great set of ideas, and I really do point you to this beautifully written paper. So I don't need to go through this. Basically, I'm just repeating what I said before, but how it works. So when this was done, the blue MOTs were made. YO, Agila, SRF, this was at Chicago, I think. And then this is Imperial. And they work really well. Great idea. So we were out wanting to like do this. So the idea was to make a simulation and just figure out MOTS in general, have a simulation so we could study, and decide, how these MOTS worked. We didn't really understand it fully, and whether we could do some interesting things with it. And so what was discovered through simulation is that there were the students who were doing the simulation, they were playing with some parameters, and they found a case where all of a sudden the cloud it got smaller in the simulation. So that led to the basically kind of basic understanding of that, and led to the experiment. The experiment matched the theory. So we got this great compression in calcium monohydroxide. And here's the basic explanation. I have a movie, but I like this diagram better. So the explanation is here we have just a one-dimensional picture. We have a lambda over 4 plate. We have typical MOT beams with polarization switch going back and forth. But now we're going to put on 2 frequencies. So we just think of this as a 2-level system. And instead of Blue tuning 1 frequency, you add on a 2nd frequency very close to the 1st frequency. And this was initially done in the simulation because there was some hyperfine splitting. It's like, oh, maybe, but the splitting that we're talking about here is like 1 megahertz. It's actually narrower than the line width. So it's like, probably shouldn't do anything, but it did in the simulation. And so what is happening is that if you look at each one of these components, you have a sigma plus and sigma minus on one side for a given frequency. So here's the frequency splitting delta. You have this component interfering with this component, giving a wave which is moving this way. This component interfering with this component, which is a wave that's moving this way. So you have these waves moving like this towards the center of the MOT and then through it. But the detuning changes. The detuning of these transitions change depending on which side of the MOT you're on. And so what it means is that preferentially the molecules are going to be interacting with this wave if they're on the right-hand side, this wave on the left-hand side. And what are these waves doing? They're doing subdoppler cooling. It's a blue MOT. So they're doing subdoppler cooling, except it's subdoppler cooling in the moving frame, which is moving at about 1 meter per second. So you have this slow belt that's moving. And if it becomes, how does it become a conveyor belt? It has to move, and then a conveyor belt, you drop it, you put the product on one side, it moves, and then you drop the product on this side. So it doesn't help if the conveyor belt just moves and just keeps on moving and goes out the window, right? It's got to somehow deposit them in the center. And it does exactly that because the detunings start to equal, so they cancel out. And so here's a sample trajectory, an early sample trajectory. Here's the position of one particular molecule as a function of time. It's moved in from outside and deposited here. Here we go. We're starting out of the edge of the trap. It's out here at the edge of the trap at low velocity. It's grabbed, it's moved along the conveyor belt, and then it's deposited into the center. And here's a simulation. Here's position. Here's velocity. And you can see that there's a cloud. You start with a cloud initially this big, and they'll get pulled in towards the center. And you kind of look carefully. This is doing exactly what you expect. You're kind of grabbing them. Low velocity, then you move them. Higher velocity, then you leave them there. And this is the experiment for calcium monohydroxide. You can see the cloud very diffuse and then it collapses. So this was the paper, and the cloud radius is now 60 microns instead of say 150 microns, which is typical for regular blue moths. And the density of around 10 to the 9 per cubic centimeter. I will say this is, if you had told me we'd be looking at data like this for calcium for a polyatomic molecule like 2 or 3 years ago, I would have said, I'll put it in a proposal, but it really happened. We're actually seeing collisions in CaOH. Those are ultracold, single quantum state polyatomic molecule. Oh, thanks, collisions. So it's just amazing. And note the density, 10 to the 11th per cubic centimeter. Very recently, we applied this to calcium fluoride. It worked like gangbusters. Here's the time after turning on this conveyor MOT. Here's the size of the cloud. And here's the density of molecules, above 10 to the 10th per cubic centimeter. We have 2 papers that just put on the archive last week. This paper about calcium fluoride conveyor MOT, and then we have this paper, which is really very in-depth theory and simulations to really figure it out. And we're able to play on these simulations with new approaches of using this basic idea to maybe improve things. And this is a typical plot. Tried some more complicated scenarios. You see some forces and accelerations that went into the paper. Right now, this is at 10% efficiency going from the MOT to the ODT, but it's limited by our small ODT. We didn't design the experiment to maximize it, and we're almost sure we can get this close to unity by using a bigger ODT. So now, part of my point is, if you have future experiments that are quoting that to get 10 to the 5 or 10 to the 6 molecules into an ODT, you can believe it. I think we have the tools to do that now. Okay, that's the group, and this is the RAX team, which is RAX is a collaboration between Harvard and MIT. Ron Garcia Ruiz, I think, oh, you heard that yesterday, Ron Garcia Ruiz and Nick Hustler. And then here's the group. Okay, thank you.
Thank you for very helpful. We take one question.